Welcome to the third lecture in this series of lectures on purification and separation. Today in this lecture, we will continue our discussion from where we left in the last lecture. We were on to the classification of various chromatographic methodologies. In today's lecture, we will continue our discussion onto the classification of various chromatographic methods. Thereafter, we will discuss about morphological classification of chromatographic techniques based upon stationary phases, and towards the end of this lecture, we would be discussing about the characteristics of mobile phase which needs to be taken into account. I told you in the last lecture, chromatographic methodology rests on three primary pillars, and those three primary pillars are stationary phase, mobile phase, and the separation force, which means the interacting methodology or the interacting force of a solute with stationary phase and its interaction vis-a-vis mobile phase. Now, based upon this interaction, chromatography can be split into various kinds. To begin with, based upon the mobile phase, chromatographic methods could be gaseous chromatography or liquid chromatography. In gas chromatography, your mobile phase would be a gas. In liquid chromatography, mobile phase would be a liquid. Going further, let's consider this gas as a mobile phase. A stationary phase may be a liquid or a solid. If the stationary phase is liquid, the force of interaction is partition, and that chromatography would be called gas liquid partition chromatography. If the stationary phase happens to be a solid, the force of interaction would be adsorption, and the chromatography would be called gas solid adsorption chromatography. This stationary phase can also be a bonded liquid. Now, what is this bonded liquid and how it is different from a liquid? Basically, it's not very different. What happens is, it depends upon the type of column used in chromatography. If you take, for example, a column which is open and tubular, and then that open tubular column is coated with a layer of a liquid, it would be just called a liquid stationary phase, and the chromatography would be called gas liquid partition chromatography. Now, in certain cases, especially in HPLC columns, what happens is, we do not just take an open tubular column. Instead, there is a solid particle taken, and those solid particles could be, for example, diatomaceous earth. Now, those solid particles are then coated with the liquid. So, this coated particle is then impregnated in the column, and such a column would be having impregnated liquid as a stationary phase, and the resulting chromatographic method would be called gas liquid adsorption partition chromatography. The same thing will extend for a liquid as a mobile phase. So, with liquid as a mobile phase, if your solid phase as a stationary phase is liquid, the chromatography would be called liquid liquid partition chromatography. Likewise, if stationary phase is a solid, the chromatography would be called liquid solid adsorption chromatography. It can also be called affinity chromatography based upon the nature of the solid, and as we would progress, I'll tell you the difference between adsorption and affinity chromatographic methods. Again, if the liquid is impregnated liquid, it would be called liquid-liquid adsorption partition chromatography. This stationary phase can also be an ion exchanger. We will discuss this also in a little bit details, but for the time being, the system would be called liquid solid ion exchange chromatography. And also this stationary phase can be a polymeric solid, and the method it incorporates for separation is size exclusion. In this case, the chromatography would be called liquid solid size exclusion chromatography. So it's very simple. Let me now take you to some of these methods of separation in a little bit details, which we call the force and motivation for separation. To begin with, I would take you to adsorption chromatography. In this case, the solid would be adsorbed onto the surface of the stationary phase, as is evident, and there is this obvious equilibrium between solute particles which are adsorbed onto the surface and the remaining ones which are there in the mobile phase. Secondly, talking about partition chromatography, when your stationary phase itself is a liquid. So now here you see this liquid layer coated on an inert solid. Now your mobile phase, the solute particles have partitioned themselves into or between this liquid stationary phase and this liquid mobile phase, and hence this is partition chromatography. Moving forward, I mentioned about ion exchange chromatography, a very important method of chromatography as far as separation of charged molecules like amino acids and similar kind of structures are concerned. In this case, your stationary phase should have or must have some immobilized charged ions. Those ions could be cations or could be anions. In this particular diagram, we are seeing a stationary phase having immobilized cations. So now your solute, which would contain a mixture of cations or anions or other charged particles, would once go through this stationary phase. So as you know, opposite charges would be attracted to each other. Hence, negative charged particles of that solute mixture would get attracted or would interact with the cations of this ion exchange stationary phase, and then the like charges would be repelled and would be eluted first. So this makes for ion exchange chromatographic method. Coming next is size exclusion chromatography, another very important chromatographic tool to separate large bulky macromolecules. So what happens here? In this case, you would select a polymeric material. Now there is a property of polymeric material, after it gets swollen, it tends to have a lot of pores or cavities inside. Those pores or cavities would be of specific uniform size. So let's consider you have a mixture of components as is being shown here, black represented by small molecules and large molecules are represented by these red circles. So now those pores probably can house only small molecules because of their size. Hence, as you would notice, inside these cavities of the polymeric molecules, the small molecules will reside or will stay for some time, whereas large molecules will just get filtered out and would be eluted first. So, this is about size exclusion chromatography. And coming last is affinity chromatography. Affinity chromatography is something akin to the interaction of molecules like antigens with antibodies. So, let us take the same example. Let us believe this stationary phase is containing some antigens shown by these structures here. And now you have a mixture of antibodies in the mobile phase. This particular antigen tagged onto the stationary phase would be able to retain only one type of antibodies, whereas all rest of the structures in the solute mixture would be eluted out, and hence it would separate the mixtures. Now, this was broadly about the force which acts and separates, and the force which is behind separation methodologies in chromatography. There can be another classification, and that classification would primarily be based upon the morphology of the stationary phase. What we have seen so far, it is about the characteristic of the stationary phase. I told you that if a stationary phase could contain ions, in some case it could contain a liquid which would engage in partitioning. It could also contain some bulky molecules. So, that was all about the characteristics of the stationary phase. But now we are moving on to another classification of chromatographic methods, which is primarily based upon the morphology of the stationary phase. It means what shape you are making of a stationary phase, right? To understand that, there are basically three kinds of chromatographies possible based upon the morphology of the stationary phase. First is paper chromatography. Now, in paper chromatography, your stationary phase acquires the morphology of a paper. So, what is basically done here is you take a rectangular piece of paper and a mixture of solute is sported, and we would see in a video coming up soon in the presentation how the mixture of solute is sported onto such plates or paper. All right. So, it is sported onto the paper, and that paper is dipped inside a closed chamber, and that chamber is saturated with a mobile phase. Now, the paper strip should be dipped just to a length which just the tip of the paper should be dissolved in the mobile phase. So, gradually the solvent would rise up, and that would make those solute particles interact with the stationary phase, which is paper in this case, and based upon their differential interactions, by the time your solute reaches the top, the particles would have been separated. So, this is about paper chromatography. But let me make an observation here, something which will be important for you to understand. When we compare the other two methods of chromatography, which is the column chromatography and thin layer chromatography, both the methods are one step ahead from paper chromatography. You know why? So, let us try to find out what is it which makes the other two methods advanced than this method of paper chromatography. In the other two methods, which is thin layer chromatography and column chromatography, you can pick, shop and decide the type of stationary phase, which stationary phase you would want, right? But in paper chromatography, this leverage is not provided to you. So, in paper the stationary phase will remain the paper, right, which is just cellulose and other such macromolecules. But in case of thin layer chromatography and column chromatography, broadly you can pick two types of stationary phase. In one case, what you can do, you pick a stationary phase which is very polar. It is more polar than the substances to be eluted. If you are using this type of stationary phase, the chromatography is called normal phase chromatography, and the column or that thin layer would be called normal phase column or a normal phase TLC, right. On the other hand, you can also go and pick a stationary phase which is very non-polar, maybe more non-polar than the solutes to be eluted. If this is the case, we are talking about a reverse phase chromatography. It would be respectively called reverse phase column chromatography or reverse phased TLC. Now, there is something about the mobile phase. In a normal phase column, you would require your mobile phase to begin with would be a non-polar mobile phase, and I will just explain why you would need a non-polar mobile phase, and you could gradually increase the polarity of the mobile phase. Likewise, in the reverse phase column, you would start with a mobile phase which is very polar, and gradually you would go down the polarity. Okay. The solutes in both cases can be non-polar to polar. We would discuss this aspect of the mobile phase as we would progress now. So, before we move on to the mobile phase characteristics, let me explain this normal phase and reverse phase in a little bit more detail as is shown in this picture. So, in a normal phase chromatography, this stationary phase is generally silica, and as you know, these silica particles on the surface would be impregnated with these hydroxyl groups. So, basically you are looking at a surface which has polyhydroxy molecules, polyhydroxy functionalities on the surface, which makes the whole stationary phase extremely polar, right. Now, in a reverse phase, the same silica can be used, the only thing is it would be reacted with some long chain hydrocarbons, so that instead of these polar hydroxy compounds, you have those extremely non-polar long chain hydrocarbons in a reverse phase stationary phase. So, as we were moving up in the discussion about thin layer chromatography and column chromatography, I will now just show you another video which will tell you about thin layer chromatography. So, what we do in thin layer chromatography, we would believe that this is one of the molecules to be separated out of n number of molecules present in the solute mixture. Okay. Now, what we would do, now see this very carefully, I was mentioning about the process of spotting, and this is the process of spotting. So, you put a spot of mixture of solute and then dip this plate inside a chamber which is saturated with mobile phase. Now, as the mobile phase would gradually start to rise, solute particles would start to move, but their speed would vary depending upon their differential interaction with the stationary phase. And by the time your solute, the solvent particle moves up, all the solute molecules have been separated, and here we get the solute particle we wanted in the beginning. Let us look at it one more time through this slide. I would rather keep you focused onto this central spot on this TLC. This central spot, if you notice, contain a mixture of solutes, at least two solutes. let us assume we are talking about a normal phase chromatography. So, your stationary phase is a normal phase silica. Now, in a normal phase, I told you, you would start with a known polar solute to begin with, right? And it is because you would want maximum polarity difference between a stationary phase and your mobile phase, right? So, you would pick out a solvent which is, in your opinion, the most known polar one. Now, what happens if you elute it with 100% hexane? It means all the known polar solute. After it is run, the solvent reaches this front, you notice that there is hardly any separation between the two solute particles. In the second case, now what you do, you make a 50-50% mixture of ethyl acetate and hexane. Ethyl acetate is, as all of you would appreciate, is much more polar than hexane. So, you have increased the polarity of your mobile phase. What it has done? Now, if you run the solvent mixture, you notice that there is an obvious and significant separation of these two solute particles in this system. If you further increase the polarity of the mobile phase, in this third slide it has been increased to 100% ethyl acetate, you would notice that again your separation is not good, since both the solute particles have moved up. Now, what it tells us? It tells a couple of important points, but before I make those points, I will just finish up with the last pending method of chromatography, which is column chromatography, which in principle is exactly similar to TLC or paper chromatography, the only difference being the morphology. And in this case, the stationary phase acquires the morphology of a column. You do not put a spot, but you pout down or add a sample on the top and then flush it with solvents, which is your mobile phase, and gradually over a period of time, depending upon differential interaction of your solute particle with the stationary phase, you would note that some particles, or you would note these band formations, which means some particles have eluted fast and other particles have lagged behind, and one would start collecting the solute particles, pure solute particles, and hence separation takes place. So, you would appreciate that this in principle is exactly similar to what we saw in a TLC and also what we saw in a paper chromatographic method. Now, the point I was trying to make during the TLC, that demonstration and my explanation about TLC, although we had seen that it is the differential interaction of solute particles with the stationary phase which would make them pass through differential speeds across the column, it is nevertheless important to also look for the right mobile phase if you want a good separation of your solute mixture. What it means? It means that there is an effective interplay between mobile phase and a solute and a stationary phase, and also a stationary phase and a mobile phase. So, there is this interplay of interactions, and you cannot overlook any of the three if you would like to have your solute mixture separated in a good way. So, an eminent question which comes to our mind is, if it is so difficult, which mobile phase to pick, right? Now, as I told you, especially in case of liquid chromatographic methods where your mobile phase is liquid, and in a normal phase chromatography, one would start with a low polar mobile phase and one can gradually increase the polarity based upon hit and trial. Okay. The question would still remain which solvent to pick. Okay, if I am speaking about less polar and then more polar, so which solvent is less polar, which one is known more polar, and is there such a list available to us as chromatographers? In gas chromatography, this situation is much more simpler, simply because what you need to do, one needs to start with less flow rate of the gas, if gas happens to be the mobile phase, and then if depending upon how solutes are coming, one could always increase the flow rate. So then changing the flow rate is easy, but changing the polarity, one would always be mused as to how one can control the polarity. Polarity of a mobile phase depends upon what is called their eluting strength, and there is a series of mobile phase or solvents available to us, and this picture is again applicable to normal phase chromatography, which tells us which mobile phase has a capacity to strengthen the elution process. For example, one could start with the least polar ones here down in the series, pentanes or hexanes or dichloromethanes, and you would always expect your solute particles to move slow, right? Whereas, if one would start increasing the mobile strength from DCM to chloroform to ethyl acetate and to methanol, one would always expect the solute particles to move up quickly. And that had precisely happened. If you could recapitulate or recollect the picture I showed you with TLC, you would remember going from hexane to 100% ethyl acetate, all the solute particles moved quickly. Water is not used in a normal phase column or in a normal phase chromatography, whereas this series would work just the opposite way in a reverse phase column, and in a reverse phase column water is our primary choice. So then the next thing is, now we know that there is a mobile strength, their eluting strength, and a range of mobiles which we can pick, but then how to pick those solvents? There are two ways in which those solvents can be picked as mobile phases in a chromatographic elution. One way is what we call isocratic elution. In an isocratic elution, addition of a solvent mixture of fixed composition is done or retained during the whole process. Again, as we saw with the TLC picture, you could remind yourself that it was an isocratic elution. In first case, we run the solvent or the column with 100% hexane. In the second case, we run that TLC with 50% of hexane and 50% of ethyl acetate, and in the last case, it was run with 100% ethyl acetate. The second is gradient elution, and then gradient elution again can be continuous. In continuous gradient elution, we tend to change the composition of mobile phase over a period of time, and that is uniform, that change is uniform. For example, one would fix a program in which in a TLC one would start with hexane for 5 minutes, and then that would be changed to, let us say, 20% ethyl acetate and hexane for another 20 minutes, and finally there would be entirely ethyl acetate for another 20 minutes. So that programming is a continuous gradient elution. And then there is this stepwise or fractional elution, in which this change is not continuous. There is a sudden change in composition of the mobile phase, which would be followed up by a period where mobile phase would be held constant. So this is about elution methodologies vis-a-vis the mobile phase. So what we have seen and understood so far, we have understood these 2 points. First point is, our separation is it significantly depends upon the stationary phase, the type of stationary phase, okay? And also it significantly depends upon the type of mobile phase. Now the next question which should come to our mind is, knowing all this background, how to make our peaks well resolved. If there is a mixture of components, let us say 3 or 4 components, what we should be doing which would make all those 3 components appear at significant distances. This question I would like to take up in the following lecture. Number 1, resolution. That would start with retention times and what roles would retention times play in resolution of a peak. And then we would look at various factors and we would come across some more terms like capacity factor and plate theory and plate numbers, and how there is an interplay of those factors which would eventually make the resolution better. I hope you enjoyed this lecture and I look forward to have you with me in the next lecture. Thank you very much.